Hi, I'm George Zidisopoulos,
And I'm Ryan Wu.
and our project looked at using nanoparticles and electrostatics to create a novel, efficient solar cell. So today, 20% of the world has little to no access to any electricity at all, and a majority of the places that lack electricity are located near the equator where solar energy is already widely available. Unlike traditional sources that have a main plant where power is produced, solar energy can be created where it's needed, making an electric grid unnecessary. First generation solar cells generate power using a single p-n junction, but their efficiencies are limited because they only have a single band gap. Third generation solar cells are currently less efficient but have the ability to use multiple band gaps and absorb a wider range of light.
This study aimed to create a solar cell with the most optimal power output characteristics. We utilized co-adsorption of quantum dots in conjunction with a graphene counterelectrode. The quantum dots were deposited in a novel electrostatic field to increase adsorption. Factors that influence cell efficiency, such as power, absorbance, and temperature, were also tested. Before we looked at studying quantum dots, anthocyanin dyes were used in conjunction with a carbon counterelectrode to test that co-adsorption is more efficient than having individually deposited dyes. Under white light, the raspberry-blackberry combination produced the most power at 0.26 milliwatts, proving that co-adsorption of dyes can be used to increase efficiency.
So when looking at the quantum dot solar cells, three different size dots were used: 4 nanometers, 5 nanometers, and 6.6 nanometers, each having an absorption peak at a different wavelength: 560, 650, and 750 nanometers respectively. These cells were tested with both a carbon and a graphene counterelectrode.
The highest power output came when the 6.6 nanometer cell with a graphene counterelectrode was tested under white light, producing on average 0.29 milliwatts of power. Graphene counterelectrodes produced on average 3 times more power than carbon counterelectrodes. The cells that had quantum dots that were co-deposited were able to absorb more light from multiple wavelength groups. In every group tested, cells that utilized the graphene counterelectrode outproduced their carbon counterparts. In addition, graphene's flat hexagonal lattice allows it to have low charge transport resistance that controls the electron transport in the electrolyte-electrode interface, allowing for charge to cycle through the circuit much more effectively. In addition, graphene has a small band gap, allowing it to be an effective conductor.
So compared to regularly deposited quantum dots, cells deposited within the electrostatic field increased their power outputs by more than 160% and reached efficiencies of around 10.3%. We got the idea to experiment with electrostatics when we were learning about electrostatics in physics. And we were learning about how differently charged particles interact with each other, and we were curious to see if you could apply this to depositing quantum dots in these types of solar cells.
So depositing the solar cells in an electrostatic field allowed for the quantum dots to be absorbed more effectively into the TiO2 nanostructure. The positive terminal attracted the quantum dots' electrons, creating an induced dipole, and allowed the negative terminal to draw the now positively charged quantum dots into the TiO2. These solar cells were able to outproduce the regularly deposited quantum dot cells by more than 160% and reach 10.3% efficiencies.
10% efficiencies are really good considering that most dye-sensitized solar cells only have efficiencies of around 4%. Because of the ability to absorb multiple ranges of light, third generation solar cells have the potential to overcome the limits that traditional solar cell technology has and make solar cells much more viable, especially in places where a lot of people aren't able to get the electricity that they need.